Hey guys, welcome back to weld.com. So today we're going to talk about the basics of plasma arc cutting. So we're going to go over all the consumables, how to tell when they're bad, what types of consumables to use. We're going to go over the settings for the machine. We're going to cut some different types of materials. So the first thing we want to talk about is what is plasma. Okay, plasma is the fourth state of matter. So you have solid, liquid, gas, right? That's three states of matter everybody's familiar with. And then plasma. It's just a superheated column of gas. So lightning is considered a plasma. The plasma column is a 40,000 degree Fahrenheit heat. So within this system, we're going to use a transferred arc system, meaning we have to have a workpiece clamp, we have to have a torch, there's going to be an electrical circuit, electricity is going to flow through that circuit, and we're going to be able to cut any material that's electrically conductive. So it doesn't matter, steel, stainless, aluminum, doesn't care. As long as it's electrically conductive, we can cut with it. Whereas with oxyacetylene, it has to contain iron, right? Because oxyacetylene is a chemical reaction. It's basically an accelerated rusting process, so it's limited to items that contain iron. So you can't cut non-ferrous items like aluminum or stainless steel, chromium, nickel, anything like that. So there's a lot of advantages with cutting with plasma cutting. For instance, we have a smaller heat effective zone because we don't have to preheat. We're running 40,000 degree Fahrenheit plasma column, so we're going to cut through that piece of material a lot faster. Some of the limitations with it, it's not as portable as the oxyacetylene kit. I can pick that up, I can put it on top of a building, no problem, it's a self-contained unit. With plasma arc cutting, I have to have a power source and I have to have air, whether it's a compressed gas in a cylinder or shop air. So today for our demonstration, we're going to go ahead and use shop air. That's probably what most of you have at your disposal. We have a Hypertherm Power Max 105. Now some of the settings that we're going to use, they're not going to be the same for what you have at home. I don't know what you have at home, so I can't recommend what amperages you're going to cut on, the amount of air pressure that's going to go through there. I'm just going to show you how our system works, and I'm going to refer you back to your user manual to find out your cutting speeds and your air pressures that go in your machine, because I don't want to recommend something and then you overcharge it with the air. So let's go ahead and get started. We'll talk about the machine. We're going to go ahead, hook everything up. We're going to build our torch, and then we're going to make some cuts. So the first thing we're going to do is plug in the air. So we have 100 PSI coming into the system. On this system specifically, this is 135 PSI max. So we're going to make sure we don't exceed that. This machine is actually pretty cool because it actually regulates the air pressure coming in off the amperage that's going to be put out. Your machine may vary slightly, so make sure you check your user manual for the air pressure settings as well as your amperage settings for the type of equipment that you have at the house. First thing we're going to do is just plug in the air hose, very simple. Now in here we have a filter. You want to have like an air dryer, filter, all that good stuff in place, because if you start getting moisture in your lines, it's going to come out in your torch and you're going to burn up your consumables a lot faster. So if you notice that you're pretty proficient at the cutting process, but you keep burning up your consumables, it's probably because you have moisture in your line. So hook up an air dryer. They make little attachments that go on the back end that'll kind of help prevent some of that stuff from getting in your lines. Next thing, let's go ahead and take a look at the front of the machine, and we'll start setting up the accessories, the attachments that go with it. So the first thing we're going to hook up is our workpiece clamp. It's not a ground clamp. I mean, you can split hairs, get technical about it. It's just a workpiece clamp because plasma cutting is DC negative, meaning that when I hook the workpiece clamp up, I'm actually hooking up to the positive. The cool thing about this is you can't screw it up, so I can't put it on the wrong polarity. I can't put it on reverse polarity, even if I wanted to, because the attachment points, they're completely different. The torch is going to plug into this hole, and the workpiece clamp is going to plug into here. So you can't screw that up, right? Even a welder can't mess it up. All right, so let's talk about all the consumables that go in here. The first thing, if you notice, on top of most machines or on the side, you're going to have a little diagram with part numbers and descriptions of what everything is. That's just going to make it a lot easier for you to order it. So the first thing is the swirl ring. Swirl ring is actually going to direct our air down through the torch, and it's going to create a counterclockwise direction for the plasma column to follow. So it's just going to make it a nice cylindrical shape of the arc. Right here's our electrode. Electrodes are typically made out of tungsten or hafnium. You can tell when they start getting bad because you're going to develop a deep pit in here. Anything after a depth of about 1 millimeter, that's about time to throw the consumable out. But if you're less than 1 millimeter, or the equivalent of a 32nd, it's still good. So don't throw these away until you reach that depth. That's just going to slide in here like that. This is our nozzle. Now note, this nozzle is 105 amp for our system. Make sure you have the correct nozzle that you intend to use when you're cutting, because if I ran like a 45 or 65 in here and I ran 105 amps on my machine, I'm going to burn this nozzle up. Now nozzles, they kind of get, whenever this hole up here starts getting elliptical, or it has a circle in there, or dented, damaged, cut up, burn up, it's time to change that out. This is something you don't want to make contact with your material. Okay, you should stand this off roughly 1/8 of an inch from your material. We're going to cover that when we get into cutting, but make sure that this doesn't make contact with whatever material you're cutting, because it's going to tear that orifice up. Once that orifice is all messed up, your cut quality is going to go downhill really quick. All these pieces go in here just like this. You really can't mess this up. If you do, the torch won't work. You'll get an error code on every machine I've worked with. If these aren't in place, if something's missing, this torch will not fire, because it has different safety measures in here. I have a retaining cap right here. This is just going to hold everything together, and then we will take our shield and put that over top of here. Now this is a drag shield. Notice it's got like a crown on top of it. I'll be able to put this right up against the material and won't have any issues with that. Notice there's little air ports around here, not like where airplanes fly out of, but there's little ports where the air comes out, and that's going to keep all my consumables shielded as I'm cutting. So I'll slide this over top of here, lock this down, and again, this I'll be able to make contact with the material. It's going to stand off a distance that's going to keep that nozzle protected on the inside of the torch. So depending on the thickness of the material you're going to cut, you're going to swap out your consumables. So you have like 45, 65, 85, 105 amp consumables. Today we're going to be using 105 amp consumables just because that's what we have on hand. We're going to cut a variety of material thickness. We'll be able to do that all based off of 105 amps. Unlike welding, where I need specific amperage for different thicknesses of material, my amperage is going to stay constant depending on the type of consumables that I put in there. The only thing that's going to really change is my travel speed. So if I have thicker material, I'm going to cut slower. Thinner material, I'm going to cut a lot faster. And I'm going to show you how that works when we get over here to cutting the material. So now that we're plugged in, we're going to go ahead and turn this on. I prefer to plug the machine in after I've got everything hooked up to it. This is my personal preference. I think it's a lot safer that way. So we're at 63 amps right now. I'm going to go ahead and crank it up to 105 because I have 105 amp consumables in here. Now you'll notice that I have a selector switch over here. The first one is, it's got like little spaces in it. That's for cutting expanded metal. So if you have perforated material, expanded metal, anything like that, this is going to be the appropriate setting. If I have solid material, like I'm cutting lines or shapes out of solid stock or a flat plate, I'm going to go ahead and use this setting here. If I'm going to do gouging or anything like that, I'm going to move to this last one. You can kind of see it's at an angle. And then the last one here is just a trigger lock, kind of like 2T or 4T on your foot pedals and finger switches on your TIG torches. Very similar. I pull the trigger and let off. That pilot arc is going to stay lit until I pull that trigger again and then let it go. If you're doing long runs, that's great. That's probably where you would use that. Long runs on material, anything like that. I'm going to go ahead and set it here for solid material, and we'll hop on over here and we're going to go over some of the consumables one more time just to kind of explain, and then we'll do some cutting. Okay, so let's go ahead and talk some worn out consumables first. So this right here is our electrode. See how we have this big divot in here? That's bad. That's not what you want. So anytime it exceeds about a 32nd or 1 millimeter, you want to go ahead and throw this out. Now here's a nozzle that's seen better days. Okay, it's kind of well worn. The orifice, the cutting orifice in here is kind of wallered out. Yeah, that's a word, wallered. Once it's tore up like that, it's a good practice, good idea to swap both of these out at the same time. The manufacturer recommends that anytime you swap out your nozzle, go ahead and swap out that electrode and vice versa. It's a drag shield. I don't know what happened to it. Just laying around the shop. Looks like it's seen better days. Got some melted areas in here. That'd be a good time to go ahead and swap this out as well. Remember, it's okay if this piece makes contact with the material. It's not part of the electrical system. So you can make contact with the material. That's exactly what it's designed for, to keep that standoff distance, the appropriate amount away from the material while you're cutting. But it's probably a good time to go ahead and swap this guy out. So let's go ahead and talk PPE real quick, because with any job that we're going to do, safety is always first. Wear dry garments, so welding jacket, welding caps, always a plus. Safety glasses, as we discussed in our last video. I prefer to use a welding hood, just for the simple fact that I'm going to deal with 105 amps here. So Infrared glasses, while they're great, these are awesome for oxyacetylene cutting. This is not something I would use if I was going to be doing plasma arc cutting, anything probably above 40 or 50 amps. So because we're using 105 amps, I'm going to go ahead and use the shade 9 on my welding hood. And then we're also going to make sure that we wear leather gloves. Again, stay away from the synthetic fibers because they're going to melt. And when they melt, they're going to melt to your hand. You're just going to have a bad day. Something with a little bit of dexterity, because on here we have a safety switch. You want to be able to get your finger up underneath there. So a big gaudy pair of arc welding gloves probably aren't the best things to use. I'm going to reference my manual here. It says for 105 amp consumables, which we have in the machine right now, mild steel, I'm going to cut some 3/8 plate. It tells me I need to run about 94 inches per minute. So how do I gauge that? This is something you're going to have to do visually. So if you're cutting too fast, you're going to notice all your sparks are shooting out away from you or in the opposite direction that you're cutting at a pretty steep angle. You want them to come out slightly, probably about a 10 to 15 degree angle from the bottom. If they're coming out straight down, you're cutting too slow. Okay, I know that sounds counterintuitive. You're going to cut too slow. You're going to have a much wider kerf, which is the area. The kerf is the material loss due to the cutting process. Doesn't matter if it's a skill saw, table saw, plasma cutting, oxy-fuel. That's what that kerf is. So that's the width we're going to be taking out of the material. So you want to make sure you're cutting on the appropriate side of the line or on the line and understand the width of your kerf. But if I cut too slow, I'm going to have a much wider kerf. I'm going to have a lot more dross on the bottom of my plate that I'm going to have to clean off later. I don't want to deal with that. I want to try to make this as less labor intensive as possible. So we'll show you 3 cuts. We'll do a too fast, too slow, and then a just right, kind of like Goldilocks. I'm going to get rid of the paper because plasma cutting, we can shoot sparks up to 40 feet. So I'll try not to cut towards the cameraman over there. You also want to check the surrounding area, especially if you're in a small garage or shop. You've got gas cans laying around, lawnmowers hanging out over there. Move that stuff out of the way or move your cutting operation to a different area. Like I said, these sparks can travel up to 40 feet, so don't cut in enclosed spaces. While we're on the topic of safety, fume extraction is a must. So we're going to go ahead and we're going to set up a vent over top of this to when we're cutting. You don't want to breathe this stuff in, especially when we get into the stainless and the aluminum, because stainless contains hexavalent chromium. Anytime we cut, grind, or weld on that, you want to make sure you have a respirator or at the source fume extraction. Same thing with aluminum. This stuff's just nasty to breathe in. You don't want to do that. So set up the fume extraction. If you're in your garage, set up a fan. If not, set up the operation outside. Just make sure you're not doing it over a bunch of dried leaves and grass and stuff like that. What I want to do now is I'm just going to measure from the outside of my orifice, or the outside of my drag shield to the inside of my orifice, and it's about 3/16 of an inch. So I'm going to offset a piece of just flat bar, or just a little piece of sheet metal, 3/16 of an inch from the line that I intend to cut. So I mean, that's kind of how you can keep everything nice and straight where you're cutting and fabricating. Just set that little offset. This 3/16. Yours is probably going to be different. Same thing if I have a standoff guide, I would actually measure from the outside of that standoff guide to the center of the orifice on the torch. That way when I cut that, I get nice, clean, consistent cut marks, and my accuracy is going to greatly improve versus trying to do this freehand. Went ahead and hooked up the workpiece clamp because you want the electrical circuit to be the path of least resistance, right? So because we're using an electrical system to do this. So notice that the workpiece clamp is on the side that's going to remain on the table. I don't want to put it on the piece that I'm cutting off, because once I cut that piece off, it falls with the workpiece clamp. I could become myself the path of least resistance. Okay, this is a high frequency system. I don't want to get shocked with it. So keep the workpiece clamp on the material, not the part that's going to fall off. Try to keep yourself out of the electrical circuit. Don't put yourself in that situation. I could hook it to the table, but like I said, path of least resistance. So the closer I can get it to the material, the better cut quality I'm going to get, the better ease of use, more efficient I'm going to be with it. So, all right, so the first one we're going to go ahead, we're going to cut this one too slow. I'm going to go ahead and shut up and I'm going to start cutting. All right, so I'm going to start right here on the edge of the material, pull the trigger, and like I said, I'm going to cut too slow, so the spark should come straight down. All right, so you can notice the travel speed is, since we're going so slow, it's kind of difficult to control the torch because I have material building up on the top of the plate as well as on the bottom, and that's just causing this drag shield to stick just a little bit. We'll go ahead and flip it over here once we're done, and we'll show you the bottom. All right, so you can see that I've got plenty of dross built up here on the bottom. It'll be easy to take off with the chip hammer, but you can see the cut quality is just crap. I've got a severe bevel on there just because it took way too long to cut that piece, right? That's kind of what we wanted to show you. That's what your cut quality is going to look like if you go too slow. Remember, one of the advantages of plasma art cutting is the ability to travel much faster. All right, so now we're going to go ahead. I'm going to set this back up. We're going to show you too fast. All right, so that was too fast. You can kind of see how the plasma coming through there was scraping off the bottom, pointing further away from me. Like I said, you want about a 10 to 15 degree tilt away from you as you're pulling it towards you, or away from the direction of the cut. So I'm going to go ahead and cut one last piece, and this should be right about the appropriate speed. And you just kind of have to judge it, as you're cutting through. All right, so let's go ahead and take a look at the samples we cut. So, got this first one was too slow. Disregard this piece right here, that was completely human error. But the rest of it, you can kind of see the cut quality on here. Not to mention the fact that it's pretty ate up as far as the bevel. Okay, so that's the cut line is, or the cut was too slow. This one here, the cut was too fast. Although it looks pretty clean. It's not bad. There's not a lot of dross on the bottom over here. I mean, there's a little bit, but nothing, we can't hit with a wire wheel or a chip and hammer. But let's take a look at that bevel, right? So we got a pretty decent bevel on there. I'd like to have a 90-degree cut, if I was cutting a piece for, depending on what I was cutting, right? And this one was just right, okay? A little bit of excessive dross on the back here, but the cut quality as far as the bevel is much better. Much closer to a 90-degree angle on this one. So, and a lot of this stuff, I mean, we're kind of nitpicking. I mean, you can clean that up with a grinder. We just want to show you the difference so you can identify, what's going on with your cutting. If you're too fast, too slow, if your speed's just about right. And it's going to vary on different thicknesses of material. Remember, go back to your user manual and check the cutting speeds for each thickness and type of material you're working on. It's going to be completely different if I was working on something like stainless steel. All of my travel speeds are going to completely change for depending on the thickness and the type of material that I'm working on. Same thing with aluminum or any other type of material. So that's how you cut in a straight line. Let's go ahead and move on to cutting different shapes out. Now, depending on if you want to keep the shape you're cutting out or you just want to cut a hole in something. So, for instance, I'm going to cut a circle. If I want the circle plate that I'm going to keep, I'm going to cut in a different direction than if I'm cutting a hole in the plate. Okay, so because the plasma column comes out counterclockwise, just like kind of like a router. I don't know if you ever used a wood router. I'm going to cut opposite of the direction that it's cutting out. So it's always going to have your cleanest edge to the right hand side of the plasma column. So the first thing I'm going to do is I'm going to cut a hole in the plate. Okay, so the piece that comes out of the middle, I don't care about it. I want the clean cut quality to be on the plate, not the piece that's falling out of it. In addition to that, depending on what type of template that you're using, remember we have just on this one, my personal torch side, yours is going to be a little bit different. I have a 3/16 offset, okay? So whatever that is, I'm going to have to double that for a circle, so the diameter. So I'm going to, once I get done with this, I should have a hole that's 3/8 less than the template that I have right here. So before I make that rotated cut, because I'm piercing through a plate, starting out here on the edge is fine, but because I'm piercing through a plate, if I try to punch straight down, especially on thicker material, that material is going to jump back up. It's going to clog up my nozzle or burn it, tear it up. It's just going to destroy the consumables. So what you want to do, I'm going to start off roughly at a 45-degree angle. I'll pull that trigger. Sparks are going to fly that way, so you want to be cognizant of what's over in that area. I'll rotate that up to a 90-degree, and then I can go about my business and cut that piece out. So anytime you're doing a pierce cut, start off roughly a 45-degree angle, pull the trigger, rotate up into it, okay? The hole right here on the plate, which is what I wanted, has a much greater cut quality. So it has almost a 90-degree vertical up and down cut quality, so it doesn't taper in. However, the piece that we cut out does have a noticeable taper to it. So you can see that, that's the piece that I wanted to discard. This is the piece that I wanted to keep. The cut quality is on the plate. Now we're going to go ahead, I'm going to do the same thing. I'm going to cut an outside circle, so I'm going to cut outside of this template. And what I want to do is I want to keep the piece that's going to fall out. So I'm going to start outside of the area. I'm going to do another pierce cut, and then I'll go ahead and I will cut that counterclockwise, keeping the piece that I want to the right-hand side of that pilot arc. Once I do that, the piece that falls out should have the straight edges on there, and then the plate that we're cutting out of, that's the one that's going to have the beveled edges. All right, so as you can see, got better cut quality on the piece that got cut out versus the piece that we cut it out of. There's a much larger bevel on the material that we cut it out of than there is on the piece that we actually wanted to keep. You can also tell that I need a little bit more practice because I've been getting spoiled by using the CNC cutter all the time. So it's about time I go back to the basics as well and do some freehand cutting and some cutting with templates and guides. All right, guys, hope you found this video educational and informative. Hopefully it helps you out along your journey, whether you're in school, in the shop, new to fabrication, seasoned welder that just hadn't had much experience with plasma cutting. That's pretty much it. Until next time, make your weld better than your last.